Hello trigonometry students, my name is Jamie Amy and this video continues our discussion on chapter 4, starting with the tangent function. We're looking at just a piece of this parent function. This is the tangent function on the open interval negative pi over 2 to pi over 2. Some details about tangent are that its domain is all x, such that x does not equal pi over 2 plus n many pi's, where n is any integer. At those points right there, you can see we have vertical asymptotes. The graph, which is written right there for us, the graph has vertical asymptotes at those values of x. So the domain exists everywhere except for at those vertical asymptotes. The parent function has asymptotes at negative pi over 2 and positive pi over 2. So that's this piece right here. We can see the asymptotes. But the tangent function is a periodic function, so it continues and the location of those asymptotes will change, but it'll always be symmetric. Halfway to each asymptotes are the points negative pi over 4 down to negative 1. So we're right here. Let me see if you can turn my pen on real quick. All right, so this point right here is halfway to the asymptote. It's at negative pi over 4 and down to negative 1. I think it's valuable to see the height of tangent at that halfway to the asymptote. It is negative 1. And halfway to this asymptote, the height of tangent, or its value, will be up at positive 1. Then it approaches the asymptote, as you can see. The range for tangent is negative infinity to positive infinity. You can see there are no holes, gaps, asymptotes as we travel from the bottom to the top. The period for each of these is pi. So the distance from here to here, distance between the two asymptotes, is pi many, well, the distance of pi radians. That makes it the period of tangent. The x-intercepts are of the form x equals n times pi, n is an integer still. So we can see the x-intercept, the one that we're looking at right here, is 0. So that x-intercept would be an integer 0 times pi, so that particular x-intercept is at 0. And you can find each of those by using all integers times pi. Tangent is an odd function. That means it is symmetric with respect to the origin. And that, as an identity, is for all x in the domain, tangent inputting a negative x will be the same thing as negative tangent inputting the positive corresponding x. All right, so that's a little glimpse and some characteristics about tangent. Cotangent now looks similar, but you might notice it's decreasing, whereas tangent was increasing. You might also notice it's not passing through the origin. It's kind of pushed over. So, and those would be two good and accurate things to notice. We're talking about this piece of cotangent on the open interval 0 to pi. Some of the characteristics are the domain is all such values of x such that x does not equal n pi. Again, that is where you will find vertical asymptotes. So pi is outside of the domain for cotangent because there's a vertical asymptote there. 0 is outside of the domain for cotangent because there is a vertical asymptote here. It looks solid because it's the represented the y-axis, but there's a vertical asymptote there as well. The parent function has asymptotes at 0 and pi, the two that we just highlighted. And this is, of course, a periodic function, so those asymptotes would move, but they're always evenly spaced out, which is nice. Halfway to each asymptote, we are again at a height of positive 1 and negative 1. So here, these 2 points, we're starting right here at the x-intercept, and we go halfway to the asymptote, we're at a height of 1. Halfway to this asymptote, we're at a height or a value of negative 1. The range, bottom to top here, you can see negative infinity all the way to positive infinity. The period, just like tangent, is pi. It's more obvious on this one. Distance from 0 to pi between these two asymptotes is the length necessary, or the period necessary to complete one cycle of cotangent. The x-intercepts, so that's, in this one we just have pi over 2. X-intercepts are of the form pi over 2 plus any integer times pi. So it's going to intercept, the next one would be like here. And there'd be one over here too if we were drawing multiple periods of cotangent. Cotangent is an odd function. That means that it is symmetric with respect to the origin graphically. And as far as an identity, it means that for all x in the domain, input a negative x, you'll get the same output as if you used negative of the function cotangent and inputted the positive corresponding x. To graph the cotangent function on a graphing calculator, we would need to use one of the identities. So cotangent x is equivalent to, using the reciprocal identity, 1 over tangent x, or cotangent x is equal to quotient identity, cosine of x over sine of x. So heads up for that if you're using technology to check your graphs. All right, so we've been talking about vertical asymptotes, a vertical line that a graph approaches but does not intersect. When b does not equal 1, tangent and cotangent asymptotes move. So we're taking those parent functions and we're going to have a transformation to them. So transformation, if b does not equal 1, what happens? Well, if b does not equal 1, the vertical asymptotes move. To find two asymptotes for y equals tangent of bx, where b, we don't often see it because it's implied to be 1, but if you see a number here in front of your x, like a 2 or a 1/2, then you've got to find a new location for your asymptotes. They've been shifted. So start with the asymptotes for the parent function and then divide by whatever that b happens to be. It looks like this. Oh, sorry. The two new vertical asymptotes will be at, it looks like this. X equals, here's the original parent function for tangent, and here's the other one. And you see you just divide it by whatever that coefficient is, that b. For example, y equals tangent of 3x, here b equals 3. So the two asymptotes would go from where they were in the parent function, negative pi over 2 and positive pi over 2, to that value divided by b, which in this case is divided by 3. Simplifying that, the asymptotes would now be at negative pi over 6 and positive pi over 6. Not too bad. So if you're asked to find the location of the asymptotes, check out where b is. If it's anything other than 1, make sure you divide by that number to adjust. To find two asymptotes for y equals cotangent b of x, where b does not equal 1. Same process, start with the asymptotes for the parent function and then divide by b. The two new vertical asymptotes will be at this line, x equals 0 divided by b and x equals pi divided by b. 0 and pi were the original asymptotes for the parent function. So you take the 0 and the pi, divide each of them by b, and you'll have the location after that transformation. For example, y equals cotangent of 3x. So here we've got b equals 3 again. The two asymptotes will move from the original 0 and pi to 0 divided by 3 and pi divided by 3, which is the two vertical lines, x equals 0 and x equals pi over 3. Notice the difference for tangent and cotangent. Their parent the equations of the asymptotes for their parent function are different. So you got to start with equations of the asymptotes from the parent function, which are different for tangent and cotangent, and then divide by b. Graph y equals tangent of 2x. A equals 1, which we should note, but tangent has no amplitude. We saw that the range goes from positive infinity to negative infinity. But knowing that a equals 1 helps us with that halfway to each asymptote, we're going to be at a height of positive 1, or value slash height of positive 1 and negative 1 for our tangent. B equals 2 right here. So our period is original pi over 2. That's going to change. Our asymptotes are going to move. So we start with the original asymptotes from the parent function, negative pi over 2 and pi over 2. Divide each of them by b. In this particular function, b is 2. So dividing those by 2 and simplifying, we have our two lines that represent the vertical asymptotes, which are x equals negative pi over 4 and x equals positive pi over 4. C equals 0 and D equals 0, so we're not going to shift this up or down, left or right. So going through the alphabet, just like we did in the last videos, A, B, C, and D, and we are ready to graph. Suggestion, I like to graph in this order for tangent and cotangent, B, D, C, A. So that means I would start with the asymptotes. So I sketch the asymptotes first, then shift those left or right if needed. Here we don't have to. Then shift those up or down if needed. Here we don't have to. And then I would actually draw the tangent curve. So really, like for the first three steps, first three transformations, I'm just sketching and moving asymptotes. Once I get the asymptotes in the right place, tangent and cotangent are easy to sketch between the asymptotes. So here we've got original asymptotes, we're at parent function asymptotes, we're at negative pi over 2 and positive pi over 2, but we divided that by b. So here are new asymptotes, these vertical lines, x equals negative pi over 4 and positive pi over 4, represent those. And sketching tangent between there. Halfway to the asymptote, we're at a value of 1. Halfway to this asymptote, we're at a value of negative 1. So this is one period of tangent right here. Then we just added on some others just so we can see it. It didn't say, the directions didn't say to graph like only one. So if we want to graph more, that's fine. If you did just graph the one, it's about understanding it, kind of vague on the directions, how many we needed. Y equals negative 3 tangent of 1/2 x. Here, a equals negative 3. So halfway to the asymptotes, we'll be at a height of positive 3 and negative 3. The negative means that we're going to reflect in the x-axis. So all of that is just the sketching of tangent. Let's focus on getting those asymptotes in place first. B, it's 1/2, so we take pi, we divide it by 1/2. So our new period is 2 pi. What that does is takes our parent function asymptotes, divides them each by b. b is equal to 1/2 in this particular question. Simplify, and we have our new asymptotes represented by the vertical lines, x equals negative pi and x equals positive pi. And the distance between these is 2 pi, which is noted right here with the period. C equals 0, D equals 0, so no shifting up, down, left, or right. So I have the same advice for you. I would graph in this order, B, D, C, A. So B, I would move my asymptotes to positive pi and negative pi, no shifting up, down, left, or right. And then A, I would sketch that, making sure to get a reflection, as well as a height of positive 3 and negative 3 when I'm halfway to each asymptote. Here we can see asymptotes are at negative pi, positive pi, crossing through the origin. Halfway to this asymptote, we're at a height of 3. Halfway to this asymptote, we're at a height of negative 3. And this has been reflected because the parent function of tangent, if you need to go back and look at it, is increasing like this here. Graph y equals 1/2 cotangent of 2x. A equals 1/2, so halfway to each asymptote, we're going to be at a height of positive 1/2 and negative 1/2. B equals 2, so our period is going to change from our original pi to pi over b. which is pi over 2 in this situation because b is 2. Our asymptotes are going to go from 0 and pi to 0 and pi divided by b, which in this case is 2. So the two lines that represent our vertical asymptotes are x equals 0 and x equals pi over 2. C equals 0, D equals 0, no shifting up, down, left, or right. And same advice, graph in this order, B, D, C, A. So B, putting your asymptotes in the right place, 0 and pi over 2. And then nothing to do for, so that's asymptotes in the right place. No shifting necessary in this question. So we go to A, and halfway to the asymptote, we're just making sure we are at a height of positive 1 and 1/2 and negative 1/2. And that is the graph of y equals 1/2 cotangent 2x. Graph y equals 2 plus tangent of x. Okay, so 2 in this case represents c. So we're going to translate the graph 2 units up. The rest of it is the parent function. So we're really just taking the graph of tangent and translating it 2 units up. Not stretching it, okay? Translating it. It's just sliding it. Oops. So that would look like this. Parent function, I'll just sketch it a little bit. We don't want to clutter up this nice looking graph. So the parent function was down here. And then our one transformation taking place, which is c equals 2, takes parent function, slides it up 2 units. Asymptotes remained in the same place. X-intercepts are up 2 units. Graph y equals -2 minus cotangent of x minus pi over 4. Okay, so lots of transformations going on here. Let's take them one by one. First one, a equals -1. It's invisible, but it's right here, guys. It's implied. So we need to make sure that we're reflecting cotangent in the x-axis. B equals 1. It's the coefficient after cotangent. You can't see it here either, but I'll highlight it for you. B equals 1, so there's no change. B equals 1. It does not change the asymptotes, but D might shift where the asymptotes are at. It's kind of getting ahead of ourselves here. So C is -2. That's right here. So C, this is A, this is B. C is -2, so we're going to shift our graph 2 units down. And D equals pi over 4. So that means we're going to shift to the right pi over 4 units. Okay, that's going to move our asymptotes. That's what we're getting at here. It was a little ahead of ourselves, but B will not change our asymptotes, but D will. We're going to shift them to the right pi over 4 units. Why not B? Because B equals 1. Okay, original asymptotes are at 0 and at pi for the parent function. So to shift right pi over 4 units, we add D to each of those. It looks like this. And our vertical asymptotes are represented by the lines x equals pi over 4 and 5 pi over 4. Advice is the same though, graph in B, D, C, A order. So B, original asymptotes, they don't get moved according to B, nothing. Oops. D, I do next, and that's because I need to shift those to the right, or just graph them. You figured out their equation, so just plot those and draw vertical lines through them. So that would go next. C, we're gonna, oh my goodness. C is gonna shift our graph down. Well, the asymptotes won't really move for that. We'll just, when we draw cotangent between the asymptotes, we'll make sure to move the x-intercept down 2 units. And also A says to reflect in the x-axis. All right, so here is the graph of y equals -2 minus cotangent of x minus pi over 4. I want to sketch the parent function on here. already pretty cluttered, which is why I went straight to this, but the parent function, cotangent of x, would have had an asymptote here. I'll just do a little bit, okay? That would have been an asymptote, and this would have been an asymptote. 0 and pi. Cotangent crosses through the x-axis here. It's a decreasing function, so it would have gone like this. Okay, so that right there is just one cycle of cotangent. Now, all of this transformed into, let's see, to the right, this transformed into this one, okay? So adding this one at first makes it a bit ahead of ourselves again with more information. But this one parent function of cotangent will become this one right here. How? Well, it's reflected in the x-axis, so that's why you see it's now increasing instead of decreasing. And then D moved its asymptotes over pi over 4 units. So we just took these dashed lines and we just moved them to here. I'll put an X now. And C took the dashed line, moved it to here. And then And then C moved the x-intercepts to -2. So that would be down 2, but we've been reflected in the x-axis. So instead of going from here, they are now here at the line y equals -2. Whoa, I don't know why that keeps changing on me. Secant, the graph looks like this here. Its domain is all x, such that x does not equal pi over 2 plus n many pi's, where n is any integer. The graph has vertical asymptotes at those values. So just like cotangent and tangent, secant has vertical asymptotes, therefore those x values would not be in the domain. For the range of secant, we're going interval notation here. So we go -infinity. It exists right here to -1. It stops existing between -1 and +1 though. I'm going to draw those just for some future reference. These are not asymptotes. I'm just trying to highlight where secant does not, where its range does not exist. So you can see here that it jumps from -1 to +1, which is why we use the union symbol. And then it exists again at 1 all the way up to this concept of infinity. All right, the period of secant takes 2 pi radians to complete one period. And what I'm going to do now is change colors and sketch its reciprocal graph. What's the reciprocal of secant? Hopefully you said cosine. So if I sketch cosine, it kind of helps lead us to the graph of secant. So cosine, I'm just going to do 1 so it doesn't get cluttered. Starts up here, crosses the x-axis there, minimums out at pi, crosses the x-axis, and maxes out at 1 when x equals 2 pi. So see, it has the same period. So this period for cosine is 2 pi. Secant's period is the same, 2 pi. So this right here would be 1 period of secant. They're not connected, so it seems a little maybe counterintuitive, but that right there, that's 1 period of secant, what I have highlighted in red, not using the cosine. Okay, so reciprocal identities, since secant and cosecant are reciprocals, their values are reciprocals of each other. The cosine graph, check this out right here, cosine right here equals 0. Well, anything divided by 0 is undefined, and secant is the reciprocal. So here secant would be divided by 0, therefore undefined. That is why wherever cosine equals 0, you're going to have a vertical asymptote for secant. Check it out right here again. Cosine equals 0, so secant is undefined. I'll draw another one. Maybe, I hope it doesn't clutter it up too much. Just want you to be able to see more examples. Cosine right here equals 0, so secant has a vertical asymptote. Cosine equals 0, secant has a vertical asymptote. Same period for each. Secant is even. That means that is symmetric with respect to the y-axis. This can be really helpful in identifying, like, if you're asked, is that graph a secant or a cosecant graph? Well, secant is symmetric with respect to the y-axis. So you see the y-axis right here, it's symmetric on both sides. So that might help you identify it. As far as identities, that means that secant inputting a negative x would output the same thing had you taken secant and inputted the corresponding positive x. Oops. All right, and that is secant. Now let's look at cosecant. Domain, all x such that x does not equal n pi, where n is any integer. The graph has vertical asymptotes at those values of x. So just like tangent, cotangent, and secant, they've all got vertical asymptotes. Those points, those x values are outside of the domain. The range is the same as it was for secant. And I'll highlight these again just kind of for our discussion purposes. So we can see that cosecant exists, negative infinity to negative 1 does not exist, but it starts existing again, positive 1 to infinity. Its period is 2 pi. This is one period of cosecant. There and there. That's one period. See, it takes 2 pi radians, going from 0 to 2 pi. That's what it takes to complete one cycle of cosecant. I want to do the same thing we did last time by sketching the reciprocal function. What's the reciprocal of cosecant? Hopefully you said sine. So sketching sine starts at here, nope, starts at the origin, sorry. Goes to here, crosses through, and there. Okay, so this is one cycle or period of sine, and once again, you can see wherever it hits the x-axis, its reciprocal function is going to have an asymptote. So if you can graph sine, which you guys all are very good at graphing sine, if you can graph sine, then if you're asked to graph cosecant, just start with these. Wherever you see that it crosses the x-axis, just draw a vertical dashed line. That would be an asymptote for cosecant. Other than that, it's the reciprocal of each of these. You can kind of see that this one here goes like this, and this is the opposite. Cosecant is odd. That means it's symmetric with respect to the origin. So notice here, if we were to fold this right here on the y-axis, it's not symmetric. This first u, if you will, parabola, is over here to this side of it. It's not like secant's, for example, was like this. So that's symmetric with respect to the y-axis. Cosecant is not. As far as an identity, if you input a negative x into cosecant, you'll get this, the output, should you have used negative cosecant and inputted the corresponding positive x. Let's look at some examples. We're asked to graph y equals 2 secant of 1/2 x. All right, so for these, our step process is slightly different. We're going to start by graphing the reciprocal function. So notice that we just rewrote it from here to here, okay? Just rewrote it. The only thing we changed is we changed it from secant to cosecant. Why? Because cosecant and secant are reciprocal functions. So now that we're just graphing cosine, we can use all of the steps that we had before. Sketch vertical asymptotes for where to guide. Oh, gotta finish step 1 first. We have to graph this reciprocal function. So this reciprocal function here, if I put the axis like this, we've got the parent function of cosine, but we have 2 transformations that have occurred. They're right here. A equals 2, so we're going to be amping up to positive 2 and down to negative 2. B equals 1/2, so that's going to change our period from parent function 2 pi to 2 pi divided by 1/2, which is 4 pi. So it's going to take 4 pi to graph one of these cycles of cosine. Oh man, I wish I would have moved this over here. Now I'm going to move it. Here's 2, here's negative 2. I'm going to erase the other one. I'm doing that because I see the period is stretched, so it's going to take twice as many radians or twice as much length on the x-axis to graph it. All right, and that should do it. So we're talking cosine, so we start up high. And, oh, I guess I should give myself a little more than that. If we make this 4 pi, that's what it'll take to complete one cycle of cosine. So halfway between will be at 2 pi, and cosine will minimum out. Halfway between, cosine will be on the x-axis. Halfway between, cosine will be on the x-axis. At 4 pi, it'll be at its max again. Okay. So step 1, graph the reciprocal function y equals 2 cosine, that was terrible, y equals 2 cosine of 1/2 of x. Okay, step 1, done. Step 2, sketch vertical asymptotes, and that will help guide our function. Okay, so we find, let me change, no, I won't change colors. Wherever cosine crosses the x-axis, secant is going to have a vertical asymptote. Crosses the x-axis, secant will have a vertical asymptote. Oops. And we are now ready to sketch secant. So it's not going to exist between positive 2 and negative 2, so it's going to exist above positive 2 and head toward this asymptote. And same thing here in this interval. It's going to exist below like this. What you do, you just find cosine. If it's above, then we're going to be above. So you stay up here and you graph it almost as if you were to reflect it. So like this piece right here, its reflection looks like this. So see how this cosine function really guided us? It told us where the asymptotes are. And furthermore, it told us like, okay, we're above the x-axis, so just do that. We're below the x-axis, so do that. And we're above the x-axis, so that there. All right, I'm going to erase all of my pen and show the much nicer. Erase pen. Okay, there we go. There we have the graph of y equals 2 cosine 1/2 x. That's used as our guide. Asymptotes are drawn wherever it crosses the x-axis, and then sketch the graph of y equals 2 secant of 1/2 x by drawing the typical U-shaped branches approaching the asymptotes. Looks like that. That looks much nicer than the one that I drew up for us. So we can see the period is 4 pi, we can see the amplitude is 2. We can see the parent function there. I like how they left this with a dashed line for us to see how these two work together. Let's graph y equals 3/2 cosecant of x minus pi over 2. We would do that by graphing its parent function, its reciprocal function first. So same transformations but done to sine. Then we'll sketch the vertical asymptotes, and that will help guide us to our graph of cosecant. All right, so first one, step 1. graph the reciprocal function y equals 3/2 sine of x minus pi over 2. That is right here, okay? So if you go through A, B, C, D carefully, you will end up with this graph, okay? That's the reciprocal function. Next, we see wherever it equals 0, and we know that those are going to be vertical asymptotes for cosecant. See, wherever sine equals 0, cosecant is undefined. Graphically, that means wherever sine touches the x-axis, cosecant is an asymptote, or does not exist there. There is an asymptote there. Okay? Then we're going to draw the typical U-shaped branches. Here we're above, so we're going to stay above. Here we're below, so we're going to stay below. Why? Well, if we're below, that means sine is negative. Reciprocal of a negative is a negative. Here, sine is positive. The reciprocal of a positive number is a positive number. And below again. These are called the U-shaped branches, and they approach these asymptotes, not touch them. All right, and that was step 3. Let's get their graph up rather than, oh, mine's not too far from theirs once I use their nice guide. But let me erase my pen anyway. And there we have our graph. All right, simple harmonic motion. In part A of the figure, okay, so this is part A right here. So this is what we're talking about, just this situation right here. A spring with a weight attached to it, its free end, is in equilibrium or rest position. Okay, so we have an attachment right here, and the spring, it's not moving up or down. It's at rest. This is the weight that they were talking about. Okay, all right, there's the spring. Oh, also let's point out, this is at equilibrium. So we're going to set that to be 0. So go over here, our y-axis, our value of it, or height, we're going to make that 0, okay? Okay, next. If the weight is pulled down a units and released, shown in part B, the spring's elasticity causes the weight of to rise the same a units above the equilibrium position, as shown in part C. So here, we're taking from equilibrium, taking it down to negative a. That's a distance of a. Well, what will happen when we let go of it is given it, what's the word, enough that they use the word energy, let's see, elasticity to allow the weight to rise that same distance but above equilibrium. So here. And this might start to look a little something like periodic trig functions to you. We have what we call amplitude. And remember also that we use A for amplitude. So you can see here we're using the A as well to be consistent. And then to oscillate about the equilibrium position. Okay, so here we're at equilibrium. We stretched it to here. It has the elasticity to go up to here. And then after that, it'll start to oscillate, but it won't always go to that min and that max point. It'll start to, let's pretend it went up. No, we pulled it down first. So down first, then up. But as that spring isolates, it's gonna bring itself back to rest at some point. So it might start bouncing faster, something like that. The position of a point oscillating about an equilibrium position at time t is modeled after either S of t equals a times cosine of omega t or a times sine of omega t. The amplitude of the motion is the absolute value of a, the period is 2 pi over omega, and the frequency is pi over 2 omega oscillations per minute. So I hope you can see some similarities to our ABCD process when we were talking amplitude, when we were talking about how B affects the period. You can see that here with omega. in this simple harmonic motion example. All right, let's stop now and finish the chapter 4 homework. I don't recall the numbers right off the top of my head, but it is the rest of the chapter 4 homework. All right, my name is Jamie Amy. See you all later.